Okay. Thank you for the introduction. Do you see my mouse?
Yes, you can
Oh,
see your
okay.
mouse and your
Okay,
screen.
great. Yeah, so we're going to kind of change gears and switch to a physical layer communication kind of talk. So today I'm going to talk about extrinsic neural network equalizer for intersymbol interference channels. This is joint work with my current PhD student, Xianghuang Qiu, and my previous student, Kazam. Okay, so this is the outline of my talk. So first, I'm going to introduce some background on triple equalization, then introduce some existing works on neural network-based equalizer designs. Then I'm going to present our proposed work on the design of so-called extrinsic neural network equalizer. So this work has two parts. The first part is for stationary intersymbol interference channel, and the other part is for time varying channels. Then I will conclude. Okay, so first, let me discuss some background on intersymbol interference channels. So you see the channel model here, where X is the transmitted signal, Y is the received signal, and the H represents the channel impulse response. So you can see the channel has L taps. So this is why we are going to have intersymbol interference, because it's a multi-tap channel. So in the channel model, you can see that first, we have a convolution of the transmitted signal X with the channel impulse response. Then we have also this nonlinear function G. So this is a pretty general channel model. For this channel model, see the goal of designing an equalizer is to be able to recover the transmitted signal X from the received signal sequence Y. Okay, so the goal is to somehow remove the interference so that you can recover X. So now this is a diagram for turbo equalization. So turbo equalization is a very helpful technique to improve the performance of equalization. So in this diagram, you see at the transmitter side, we have a channel encoder that encodes a sequence of information bit into a sequence of coded bit C. Then we do a constellation mapping, map it to like 16 quam, for instance. Then we transmit the symbols, the symbol sequence X over the intersymbol interference channel. Then at the receiver side, we are going to do this turbo equalization. So when I say turbo equalization, I refer to the iterative processing between the equalizer and the decoder. So over iterations, the decoder and the equalizer, they're going to exchange information. So you can see there is a feedback loop from the decoder to the equalizer. At each iteration, the equalizer is going to take two inputs. One is the receive sequence Y, and the other is coming from the decoder. So here the notation is the LA, so the likelihood, the log likelihood ratio. So the log likelihood ratio is defined as the log of the probability of a given bit being 0 over probability of a given bit being 1. So over iterations, the decoder is going to refine its estimates of the transmitted bits. So over iterations, you are going to get better LA, the prior information. Then the equalizer is going to take advantage of that improved prior. Then it's going to look at Y and LA and try to produce this so-called extrinsic information. So here in the setting of turbo equalization, it's important to use this so-called extrinsic LLR, extrinsic log likelihood ratio. So what it means is that you want the LE of a given bit that coming out of the equalizer to be independent of the prior LA of that particular bit. So the purpose of this is to remove that error propagation effect so that the turbo loop is going to perform better. Okay, so now let me introduce some related works. So for the conventional approach, typically assume that the channel is known, and the optimal equalizer is the maximum a posteriori probability equalizer. So this equalizer the performance optimum, but the complexity is very high. So it has the exponential complexity in the channel length. So in practice, we often use the so-called the soft minimum mean square error estimator, the MSE. So this equalizer has lower complexity, but the performance is suboptimal compared to the map. So in recent years, people have looked at neural network based equalizer designs. So the advantage of the neural network design is that a neural network equalizer doesn't need to assume that the channel is known. And also it can handle nonlinear channel pretty well. So if you look at the existing work, most of the work, they do this one-time equalization and decoding, meaning they do not consider turbo equalization, which is the focus of our work. And also some existing work, their design, the neural network equalizer design would depend on the choice of the channel code. So the training is done, according to a given channel code. So if you train the code, you have to retrain the neural network. Also, there's very limited work on designing extrinsic neural net equalizer. So that, as I mentioned earlier, in order to make sure that the turbo equalization works well, you want to make sure that the neural network generate extrinsic LLR. But the existing approaches does not really approximate this extrinsic LLR well. In recent years, there's also several work that are designing neural network equalizer for time-varying channels. Again, these works do not consider turbo equalization. Okay, so here is the list of the related papers that I referred to in my previous slide. Okay, so next I'm going to introduce our work for designing the extrinsic neural network equalizer for stationary channel. In our design, we propose a three-step neural network training procedure. So this special procedure is designed so that the neural network generates the extrinsic information that we need to guarantee the performance of turbo equalization. So we use a deep neural network called this DCCB. So also our design can work with any channel codes because we use an open loop simulation to train the neural network. And our results show that the proposed EXNE outperform the soft MS equalizer and can perform closely to the map, even though it doesn't know the channel. Okay, so this is the neural network architecture that we use. So it's kind of like a deep network. Our design consists of concatenated convolutional blocks. So in this figure A, you see we concatenate B blocks. So in this figure B, you see a zoom in picture for each of the block that consists of multiple layers, and we also use this skip connection. So using this, so our design is based on this proposed architecture. And also a interesting feature of our design is to use this open loop simulation. So meaning we do not need to use a closed loop setting to generate our training data. So we do not need to run an actual decoding algorithm in order to train our equalizer. So here our approach is that we would generate the prior information, because remember the prior information comes from the decoder. So we would simulate that prior information using Gaussian approximation. And the way we control the quality of the input is through this parameter IA. So IA is the mutual information between a given bit and the prior, the LA. So we generate the priors using Gaussian distributions, and we specify the quality using this mutual information IA. So from this figure, you can see that as we increase the value of the mutual information from 0.1 to 0.8, you can see that the two bit 0 and bit 1 can separate better when you use the larger IA. So this is the basis of our generation of training data. And also we use this data augmentation technique, where for each pair of a transmit and receive signal XY, we can generate multiple priors. So this way we increase the amount of our data set, our training data set. So in addition, we also do a perturbation on the receive signal Y to increase the amount of training data that we have. So this figure shows the three-step training procedure that we have. So in the first step, we generate this prototype network, where it's based on the so-called a posteriori probability, so it's not extrinsic. But in the second step, what we do is that we would use this parallel network that we trained in the first step to generate extrinsic LR that we need. Then in the third step, we would use the training data provided from step 2 to generate to train the final EXNE network. So the network that we got after step 3 is the one that we'll be using. So let me show just one simulation result using this the proposed design. So in this channel, I'm plotting the frequency response on the right. You can see it's a very challenging channel with a very severe null in the frequency domain. So the ISI is pretty significant in this case. Here we compare the performance of our equalizer, which is this black curve that's most close to the red one. So the red one is the optimal one, is the map. And our neural network performs pretty close to the optimal one. And it's about almost 3 dB better than the MSC equalizer. And the green curve here is the one that's not extrinsic. So we get the green curve by using the neural network from the first step of our 3-step design. So you can see it's very important to use the extrinsic equalizer rather than the non-extrinsic one. Okay, so yeah, since in the time of interest, we have also similar results for the nonlinear channel. Again, we see that our proposed design can perform pretty well, close to the optimal one. So now I think I don't have a lot of time left. So let me just move on to the second part on this meta EXNE. So for this part, our goal is to extend our neural network equalizer to time varying channel. So the main challenge of this part is that when the channel is changing, we need to adapt our neural network to the channel variation. But in a practical scenario, we really don't have a lot of training data. So we have some limited number of pilots, but that's pretty much it. So in this case, it's we were very interested in trying to find out whether the neural network equalizer would be able to work for the time varying channel. So in our approach, we adapt the model agnostic meta-learning, the MAML approach, to do the network adaptation. And we also use data augmentation to increase the number of training data. So in our work, we first look at the slowly time varying channel. That's mostly for the indoor environment. Okay, so in this figure, I show how we do the multi-channel training. So what we do here is that we want to train a very good meta initialization. So here we take multiple tasks. So each task is from one of the 10 base channels that we select. Then for each of the tasks, we select one channel, and we select one data block from that channel, and we select a random SNR. Then once we have chosen this particular task, we would define the so-called query set and support set. So if we are trying to equalize, say, block I, then we would define the support set to be the neighboring blocks around block I. Then we do this network adaptation using this support set. Then once we finish the adaptation, once we adapt the initial theta to find one, then we'll equalize block I using the query set. Then we compute the BCE loss. Then we update the meta initialization using the sum losses of all these tasks. So this is how we come up with a good meta initialization. Then this figure shows how we do the online evaluation. So the way we do it is we have multiple phases. So in the first phase, we just use pilot signals to do the adaptation. Then followed by using this, after adaptation, we get 5. Then we equalize each of the data blocks. Then in later phases, because we have already got decoded data, so here we kind of improve our adaptation by adapting theta to each block. So here we are doing equalization using a different neural networks specifically adapted to each data blocks using decoded data from its neighbors. So using this approach, so here, I think probably I need to skip this slide. So this slide shows the set of 10 channels that we use to do the multi-channel training. I can see that the frequency responses look quite different, right? So this gives us sufficient amount of diversity in the training data. And then just let me show one simulation results. So this is for a 5-tap channel. So the channel is changing at the fading rate of 0.1 Hertz. So if you look at the figure on the right-hand side, you can see if you look at 10 data blocks, the difference in the channel is pretty noticeable. So you go from this green curve to that deep red curve. So the channel changes quite a bit. So in this figure, we show that indeed, by using meta-learning, our equalizer is able to keep up with the changes of the channel. So here, the green, the magenta, and the red curves represent performance after each phase of our equalizer. So you can see it get pretty close to the optimal map. Well, again, you see it's significantly outperform the MSC equalizer, which knows the channel actually. Okay, so now let me just conclude. So in our work, we show that using a neural network to design equalizers is pretty effective. It shows some promising results for turbo equalization over a number of linear and nonlinear channels that we examined. So in particular, we show that we can achieve superior performance than the MSE, even though the neural network doesn't know the channel. So directions for future work would include extension of our current design to ISI channels with longer memory. And also, we are interested in designing better meta learning schemes for EX and E so that they can be applied to faster time variant channels. Okay, so that concludes my talk. I hope I didn't go over too much.
No problem.